Good morning. We're going to talk about the complex plane today. That's chapter 9.6. So this is going to be another way of graphing complex numbers. Now we understand we can't graph complex numbers on the XY coordinate grid because there's no imaginary axis. So there is something called the complex plane. So it consists of a real number axis and an imaginary axis. So complex numbers are always made up of two parts, a real part and an imaginary part. So if I had the complex number, and it's always z, because these are technically vectors, equals 1 plus 2i, what I would do is I would go over 1 on the real axis and up 2 on the imaginary axis. So it is going to look like that. And I can label it 1 plus 2i. So if z equals negative 4 minus 7i, I would go out negative 4 and down 7i. Now this is, you can think of this almost as the XY coordinate grid, but this is the real part on the real axis. This is the imaginary part on the imaginary axis. Now, the next thing we're going to do is we're going to talk about complex numbers. Now, they are in the form of a plus bi. Now, if b is 0, it's still a complex number, but it's going to be a real number. Next, if a is 0, then I'm just going to have the imaginary part, and I call that a pure imaginary number. Now, one of the most important things is we have to find the absolute value. We also call it the modulus, it's the length of the vector. So what we're going to do to find that is basically getting a phone call. I'm going to take basically use the Pythagorean Theorem. Now, the most important part when talking about finding the length of these absolute value or these imaginary numbers is I do not put this I in here. Now, that's going to be a big mistake because once we use that Pythagorean Theorem, a lot of people want to put that I in there and square it. We do not do that. All right, so we're just going to use that Pythagorean Theorem to find the length of the absolute value. So for instance, if I had 3 plus 2i, the first thing I'm going to do is I'm going to graph it out. So I'm going to go over 3, up 2. So this is 3 plus 2i. And then I'm going to use the Pythagorean Theorem to find the distance. So that is going to be z, or the distance of z, is the square root of 9 plus 4. Notice I just square these two numbers. I do not square the I. Do not square the I. So that is going to be the square root of 13. So pretty simple, just basically your Pythagorean Theorem. Now, if you had negative 4 minus 5i, I would go out actually let's make it negative 4 plus 5i. So I would go out negative 4 and up 5. Up like that. And then I'm going to find the absolute value of that. I'm going to take the square root 16, because anything squared is positive, plus 25 is going to be the square root of 41. That doesn't reduce. Make sure you reduce all your square roots. The next thing we're going to do is we are going to talk about equality of complex numbers. So if I had two complex numbers and I'm going to set them equal. Now, I have 2x plus y plus 3i equals 9 plus xi minus yi. Now, the most important part of equality is if I know I have two complex numbers that are equal to each other, I know that the real parts are equal and I know the imaginary parts are equal. Now, the way we determine a real part from an imaginary part is kind of simple. So if I have no I in it, that is real, and this is real. If it was imaginary, it would have an I paired with it. So I would have this is imaginary, and this whole thing is imaginary. So what I'm going to do to solve this is I'm going to set the real parts equal, and I'm going to set the imaginary parts equal. So I'm going to have 2x plus y equals 9, and I have 3i equals xi minus yi. Now, the easiest thing to do is just to factor out an I and divide it. So if I divide everything by I have 3 equals x minus y. Now, between these two equations, this is a system. So we talked about systems in Algebra 2. We talked about a little bit in Algebra 3 trig. So we can solve that with elimination, substitution, or graphing. So what I'm going to do is I'm going to do both elimination and substitution. So I'm going to write 2x plus y equals 9. This is elimination. And then x minus y equals 3. Kind of just flip-flop that. Now, what I want to do is I'm going to solve for a point that makes both of that true. Now, what I'm going to do with elimination is I'm actually going to add these together. Now, the reason I'm going to add them together is when I do that, that y is going to cancel out or go away. So I'm going to have 3x equals 12, so x equals 4. Now, when x equals 4, I'm going to have 8. I'm going to use this equation, 8 plus y equals 9, so y equals 1. So I know that intersects at 4, 1. So the solution set is 4, 1. When x is 4, y is 1, that is true. The next thing I'm going to do is I'm going to go back and I'm going to do substitution. Now, it really doesn't matter which one you do. It's the same thing and it gives you the same answer. So how I'm going to do substitution is I'm going to take this equation and set it equal to y. So y equals negative 2x plus 9. Then I'm going to substitute that in for this y right there. So I have 3 equals x minus the quantity of whatever y is. So negative 2x plus 9. Now, what I'm going to do is I'm going to distribute that negative sign. So I have 3 equals x plus 3x minus 9. So I'm going to combine those x's and take this 9 to one side. So I have 12 equals 4x. X equals 3. I might have messed up my elimination. I'm going to do that again, because I think I got 4. Anywho, so x equals 3, y equals, or maybe I did this wrong. Nope, this should just be plus a 2x. So this is going to be a 3. That's going to equal 4. There we go. So x equals 4. Again, I'm going to distribute. That's going to turn that positive, going to turn the 9 negative. I am going to combine like terms. X equals 4. The next thing I'm going to do is I am going to plug that back into the original. So I'm going to have when x equals 4, I'm going to have negative 8 plus 9, which is the 1. So I have the point 4, 1 again. Hopefully you can see that. Hopefully there's not a big glare on it or it's too dark. Hopefully that's better. Now the next thing we're going to talk about is going to be the polar form, or the trig form we also call it, of a complex number. Now this is going to be almost like the polar form of a number that we talked to in a polar form, or sorry, a polar form of a rectangular number or point. So it's going to be the same process. Now, it is in the form, this is the trig form. It is of, or the complex, it is a plus bi. So the polar form, so if a rectangular form is this, the polar form is r cosine of theta plus I sine of theta. Now the reason this is this is my x coordinate and this is my y coordinate. Kind of the same thing as the rectangular and polar coordinates of a point. I want to find that angle and I want to find out how far from the center that is. So if I was given negative 3 plus 4i, what that's going to do is I'm going to graph it out. Negative 3 plus 4i is here in quadrant 2. So I am going to have to use reference angles. Now the first thing I'm going to do is I'm going to find r. Remember, that is your distance away from the center. So I'm going to do that Pythagorean. Now this is going to be 5 once I solve that out. It's a 3, 4, 5 triangle. The next thing I'm going to do is I'm going to take my calculator and find that angle. Now, what I'm going to do is I'm going to go make sure my calculator is in degree mode. I'm going to take the arctangent of y over x, or sorry, that b over a. So the arctangent of the absolute value of b over a, basically your y over your x coordinate, if you will, and that's going to equal theta. Remember, that's going to give you a reference angle. So when I take the arctangent of, 4/3, remember, always take the arc of a positive, is going to be 53.13. That is applying it to quadrant 1. This is clearly in quadrant 2, so I'm going to take 180 plus the 53.13 and get 233.13. So this polar form is in the form r is 5, cosine of 233.13 plus I sine of 233.13. Oops. So that is the polar form of that number. So basically find r and find theta. The next one is going to be negative 1 minus I squared of 3. First thing I'm going to do is I'm going to find r. So I'm going to take the square root of negative 1 squared plus the square root of 3 squared. Remember, never take the I with it. So this is going to be 1 plus 3 is 4. The square root of 4 is 2. So r is 2. If I were to graph that, that's going to be out here in quadrant 3. Because it's also negative, negative. So the next thing I'm going to do is I'm going to take the arctangent of the square root of 3 over 1. That's going to be a reference angle of 60 degrees. Then I'm going to have to apply that. So I can take that in my calculator. It will give you a nice whole number of 60 degrees. Then I'm going to apply it to quadrant 3. So theta is going to be 240 degrees. So when I go to build that in the polar form, it's going to be z equals 2 cosine of 240 plus I sine of 240. And that's your polar form. Now, the next thing I want to do is I want to discuss if it's going to be, the only thing you've got to worry about is if it is going to lie on the axis. So if I was given z equals negative 3i. If I were to graph that out, it's going to go -3 on the imaginary unit, so that vector is going down this way. Now, the way I'm going to deal with that is that if I take the arctangent, this would be taking the arctangent of an undefined number, because I would have 0 over, or -3 over 0. Your calculator would give you an error, but just know that's down at 270 degrees. So r would be 3. That would be cosine of 270 plus I sine of 270. Just in your calculator, that would give you an error. So watch out for that. The last thing we're going to do is we're going to graph the following in polar coordinates, and then we're going to name the rectangular coordinates of that same thing. So this is the example. I was given 4 cosine of 11 pi over 6 plus I sine of 11 pi over 6. Well, if I were to graph that into graph it in polar coordinates, I would go out 4 and around 11 pi over 6. That's 1 pi over 6 shy of 2 pi. So it's going to be right there in quadrant 4. Now, if I wanted to express it into rectangular coordinates, what I would do is I would just basically distribute this. So basically going back to your polar coordinates, changing them from polar to rectangular, so you're going to have r sine of, or r cosine of theta plus r I sine of theta. So cosine of 11 pi over 6 is going to be cosine's positive in quadrant 4 with a reference angle of 30 degrees. So that's going to be the square root of 3 over 2. Plus for I, the sine of 11 pi over 6 is going to be a -1/2. So all my answer would be 2 square root of 3 plus, or actually minus 2i. So if I were to graph that out into rectangular coordinates, I would go over 2 square root of 3 units and then down 2 units on the imaginary axis. That is it for today.